Hi folks, today we're going to talk a little about solving the concentrations of proteins in different conformations in the native state. This question is asking us to solve the concentrations of 4 different folded conformations in the native state, given their free energies, in a 15 micromolar solution at 25 Celsius. So you can notice that a lot of these have different free energies. C is going to be the most stable. How do we know that? It has the most favorable delta G, negative 8 kcal per mole, followed by B, then C, then D, and of course the unfolded state is the least stable. The free energy change from the unfolded state is 0 because it's unfolded to unfolded, doesn't have any change. So I'm going to draw a little picture here. So A, then B, then C, and then so A is negative 5.7. I'm just going to draw that here. And then it's going to go down to 6.3, and down to negative 8, and then back up to negative 4.1, something like that. So we have our A, B, C, D, and then the unfolded is up here. Our A is at negative 5.7. Our B is at negative 6.3. Our C is at negative 8. And our D is at negative 4.1 kcals per mole. And so it should rank like this. The D should be higher than A by some amount. Then B should be lower than A, and C should be the lowest. So that's a little thing that should sketch us. So we should have the most stuff in C and the least protein in the unfolded state. Okay, so how are we going to go about solving this? Well, it's a slightly involved process here, but it's not hard, it's just some algebra. So one thing we need to keep in mind is that we have a 15 micromolar solution, and that's going to be the sum of all the conformations. Now, of course, a real protein has multiple conformations, but in the native state, that's going to be the majority of our population. So our 15 micromolar solution is going to be the sum of A and B and C and D and the unfolded state. So the concentrations of A and B and C and D and U are going to equal 15. So all we have to do is find the concentrations of all of those, and we'll be in good shape, right? Much easier said than done. But there's an easy way we can do this, and that's called in terms of 1. So here we really have 5 unknowns. We need to solve for 1. Relationship solve. And so what I like to do is I can pick 1. So the question is asking if I need to solve C, I might solve C. Here I'm looking for anything, so I just start with A. And say, what is my delta G for transitioning between A and B? Well, if we're going from A to B, then it's going to be G of B, the delta G of B minus the delta G of A. That's going to be equal negative 6.3 minus negative 5.7. And that's going to be negative 0.6. Kcals per mole. I'm going to do the same thing for all of the transitions from A. The reason I'm holding A constant here, the first thing constant, is as you'll see, it helps us to get everything into 1 unit, and then it's easy. And I'm going to go from A to C. That's going to be the delta G for C, which is negative 8, minus negative 5.7, which is our A free energy. And it's going to be negative 2.3. Then I'm going to go to D. D is negative 4.1 minus negative 5.7. So in this case, here we're going to end up with positive 1.6. That should make sense because we're going from a lower to a higher number here, being more positive. So that shouldn't be favorable for us to put, but it can happen. Okay. So that's 1.6 kcal per mole. And then we'll finally do the unfolded state. A to unfold. The unfolded free energy is 0 relative to the delta G. So the delta G for the U is 0, minus negative 5.7 is positive 5.7, correct? So that makes our life a little bit easier. Now we have all of the delta G's for all the transitions from A. So that's going to help us out. Now what we can do here is solve for our KEQs. So I'm going to scroll down a bit and give it some room to work. Okay, so our KEQ for A to B depends on the delta G from A to B. Recall this equation, delta G naught is equal to negative RT ln Q. If we're in kcals per mole, RT is negative 1.987 times 10 to the negative third kcals per mole. Kelvin times 298 Kelvin. This whole thing equals about 0.59. So you're going to see me using that. That's RT here. Over and over here. And then remember that's RT. So negative 0.59. If we solve for KEQ, it goes E to the negative delta G naught over RT, or E to the negative delta G naught over 0.592 as I did. Okay, so we're going to solve KEQ for all of these using our delta G for our specific transition. So delta KEQ from A to B is going to be E to the positive 0.6, because it starts with negative, it's a negative, over 0.592. This is E to the 1.01. So it should be pretty close to E. 2.755, yeah, so it's a little bit higher than regular E. All right, cool. That's the KEQ from A to B. So in this case, B is going to be favored because KEQ is larger than 1. But this also means, remember, product over reactant. These products here, as it's written, over A's. So product over reactant. So we're going to have 2.755 times more B there. Cool. All right, so let's do the same thing for the others. KEQ for A to C is going to be E to the positive 2.3 rather, over 0.592. So positive 2.3 divided by 0.592. This is E to the 3.88. And that equals 48.67, which is equal to C over A. Can you start to see why I have all of these solved in terms of one variable, especially the first starting variable? That means A is on the bottom. And if we convert this, we can get concentration of C in terms of A. By multiplying A across, we get C is equal to 48.67A. And now we have them all in terms of one variable. We can do the same thing up here for B. B is equal to 2.755 times A. Okay, so let's do D. KEQ A to D is equal to E to the negative 1.6 over 0.592. All right, E to the negative 2.7, which equals 0.067 equals D over A. So D is equal to 0.067 times A. So there should be less D's than A's, and we saw that up on our little diagram. Remember that D is highest in energy. So there should be a lot less D's than A because D is higher in energy than A. So A should dominate. So that makes sense. All right. And finally, let's use our unfolded. KEQ A to U is equal to negative 5.7 over 0.592. This is E to the negative 9.63, which equals 6.58 times 10 to the negative fifth equals U to A. So U equals 6.58 times 10 to the negative fifth A. So we have all of those with respect to A now. So let's go back to our original little equality. Down a little farther. Okay, 15, recall, was our total concentration. Is equal to A plus B plus C plus D plus U. And we have all of our other 4 unknowns in terms of A already. So let's just put them all in terms of A. So if we're going to say 15 micromolar is A plus B plus C plus D plus U, we can also say 15 micromolar is 1A, because A is A, right? We didn't need to solve for that. B, we said, was 2.755 of A. C, we said, was 48.67 times A. And that should make sense because C was the lowest energy. D, we said, was 0.067 A. And U, we said, was 6.58 times 10 to the negative fifth A. Okay. That looks good. So I'm going to simplify our terms here. I'm going to combine all of the coefficients into 1. 15 micromolar is equal to 1 plus 2.755 plus 48.67, 0.067 plus 6.58 10 to the negative. So if I add all of those coefficients together and leave the A, we end up with 52.49. And now we can solve for A. A is going to be 15 micromolar divided by 52.49. All right, now we have a final concentration. We have one of our 5 pieces we need to solve. A is 0.285 8 micromolar at equilibrium. So a very small fraction of one of our 4 native state conformations is at this time. Of our 15 is in A. Now what we can do is go back to our terms up here. Remember that all of these represented our conversions. So this is for B, this is for C, this is for D, and this is for U. So what we can say is that B at equilibrium is going to be 2.755 times A, or 2.755 times 2.2858, which equals 0.7873 micromolar. Let's do the same thing for C. C was 48.67 of A. A lot more here. And we should expect this to make up the bulk of it because it's the lowest energy state. So again, we're going to plug this guy in here for A. 0.2858 times 48.67. 13.91 micromolar. That's almost all of the 15 micromolar we have, and that makes sense because it's the lowest energy conformation. And finally, we got D and U. D was 0.067, it's higher in energy than A. So plug that in, 0.2858, which is A, 0.067, 0.019. Not very much in D, but at least it's not the worst off. U is the worst off at 6.58 times 10 to the negative fifth of A. 6.58 times 10 to the negative fifth times 0.2858 is 1.88 times 10 to the negative fifth micromolar. Okay, so there are our 5 equilibrium concentrations. If you recall our little picture from before, C was the lowest in energy, followed by B, followed by A, followed by D, and followed by U. So we can add these all up. Let's see if these add up to 15. The sum is going to equal 0.2858 plus 0.783 plus 13.91 019 plus 1.88. I got 15.00. Of course, if you did any rounding here and didn't round exactly, you might get something even larger than 15. That's just a rounding error. That looks good though. 15.00. Now, it's a good way to check yourself to make sure you didn't make a mistake with any of these conversions. If this thing is coming out much larger than 15 instead of just a rounding error larger, then you did something wrong. So let's walk back through what I did here to get these numbers. The first thing I did was I drew my little picture and I picked something I was going to. Here I needed to solve all of the conformations, so I didn't matter where I started. But if a question on an exam or a test or a quiz or something asks you to solve for one of them, always start with that one and go to the others, because that'll help you get it into that. So for example, if I had asked you to C, you would just not C to A, C to B, C to D, C to U. And your C answer spits out first before you get anywhere, right? So you get to this point where it would have been 15 equals something times C. Solve for that, you would have had 15.9 for C. It doesn't matter how you do this, is what I'm trying to say here. Really, it's all going to come out the same as long as you're paying attention to the system. So again, pick something, go to all the other conformations, find the delta G. It's always final minus initial. Products minus reactants, right? So here, B is our final, A is our initial. Final minus initial is going to give us our delta G for the transition. Then you use those delta G's to solve your KEQs for all of the different transitions. There's always going to be n minus 1, where n is the number of states, transitions. Then we use all those relationships to find one of the concentrations, and we plug back into the relationships, the KEQs that we had earlier, to find all of the concentrations. So hopefully that was helpful. Thanks, guys.